So in this video about integral relations over a control volume, we're going to discuss the conservation of energy in an open system. So let's consider a system like this. Perhaps it has a couple of entries, and the fluid volume, the control volume we're going to study is something like this, where we have an inlet 2 here, an inlet 1 here, and an outlet. And of course, the number of inlets of outlets is more or less arbitrary. So we had already defined the energy, and the same as in a closed system, we would have, by Reynolds transport theorem, that the change in energy over the fluid volume, which is Q in minus workout, well, that's simply going to be, if we write it first, a simplified version, the change of energy in the control volume over time, and then plus the sum of the mass going out times specific energy out, and minus the sum of the mass flow in times the specific energy in. And of course, I'm summing because there might be different number of inlets and outlets. If we write it in full generality, this is going to be d over dt of the integral over the control volume of rho and the energy is going to be 1/2 of v squared plus gc plus u dv, and then plus these terms of the inlet on the outlet. In full generality, they were the integral over the surface of rho, and then 1/2, and again the same, v squared plus gc plus u, and then times v minus vc dot n ds. And of course, this is perfectly valid. However, we'll see that there is a form that is slightly more convenient. So let's look at it. And what we're going to do is work with what's called the work of pressure. So we will split the work. We will consider two things. The work of pressure, which we will call WP, and the rest, all the sources. That, although it might be a bit confusing initially, we will still call V out, so as not to have to change too much the notation. So what is this work of pressure? So again, let's consider this tube. Okay, and we have a certain fluid acting on it. Let us consider a control volume here in the middle. It's going to be our control volume. Now, if we look at the pressure, we don't know it, but let's look at this surface here. This one is going to have a certain pressure P. And so, what we can say, if we look at a small element of this surface, it's going to have a pressure. And so we're going to have a small force here. It's going to be P times ds. But this is also moving at a certain velocity. So we can consider the work done. We'll have that there is a small amount of work in this small surface that's going to be this velocity times P times ds. Because remember, the work is always, or can be defined as how do you say, as force times velocity. Here, a small caveat: usually when we say work, remember that we always put the dot, which means that we're talking about the work per unit time, not in units of power, not in units of energy. Okay, so with that we can define we can define the work of pressure as the integral over the surface of this d work. So if we write it in full generality, this is going to be p times the velocity, and it's always going to be the change in velocity, and then, of course, dot n and ds. If we write it in slightly different form, this is going to be c, and let me write it now, p over rho times rho, and then v minus vc dot n ds. And you may be wondering why I am writing it this way. That's simply in order to be able to combine this work of pressure with the surface integral, because notice that this work here is exactly the same as we had in here. It's sort of had the same shape, but it's adding a new term. Yeah. So what we can do here now is write the conservation of energy, and that's going to be or Vc dt. Let me not write it in the integral form to save some space, and then plus the integral over the surface of rho, and then 1/2 v squared plus gc plus u. Let me save some space here. It's u times v minus vc, and then ds, dot n ds, and then finally this is equal to q in, and then the work, let me split it in these two sources. So one, let me still call v out, and then minus the work on pressure, which again I'm going to write it as the integral over the surface of p over rho times rho v minus vc dot n ds. And notice here that this term I can just move to the other side. So what I'm going to do is I'm going to cancel this, and instead put it on the other side as p over rho. And basically I'm going to call this little e, and so we're going to work in this fashion. So we can write now, and we can write a new version of the conservation of energy in this fashion. The change of energy in the control volume minus the sum over the inlets of mass in times E in plus the sum over the outlets of mass out E out, and that will be equal to Q in minus the work out. So we write it in this manner, but do keep in mind that these E's are actually these ones here, so the ones including pressure, and then the work out is this one here, so the one except for the work of pressure. And this is the equation that we will use the most in terms of energy balance. Then it will also be quite interesting sometimes to study the case, or to study the conservation of energy between two states, and then we can do the same in mass. So if we had this change of energy over time, then minus the sum mass in E in plus the sum of mass out E out equal Q in minus work out, what we can do is again integrate over time from the initial state to the final state of dt, and then the same in all of them, from the initial to the final, and then dt, integral from the initial to the final dt, and then also here from the initial to the final of dt. Basically, this term, well, we're integrating over time of a time derivative, so this is going to be the energy on the control volume at the final state minus the energy at the control volume at the initial state, so the change in energy. This is going to be mass in, so that's the total energy that's flowing in. And then plus, we can sum over all the inlets, sum over the outlets of M out, E out, which is the same as before, but just with the flowing out. And then this is equal to Q in minus work out. And again, notice that I have removed the dots. So this is a total heat or work that has been exchanged between the initial and final states. So just to remind, this is power, so it's going to go in watts, whereas this is energy, so it's going to go in joules. So it's important not to mix up the two. Okay, so with that, it's enough for the conservation of energy.